I am here. Can you see me? We both live here. But do you really know who I am? Who we are? We are 11 different nations, 11 languages, expressing identity and territory. Each sharing our strength and our story. We carry seasons, gestures, and culture for today and for our future. We are 11 nations, 11 ways of living here.
When that?
Iyo, Kanyangahaga, Mima, Abeniki,
Where's the way? He knew.
Adigma,
Then it's not bad.
Naskapi. Inui. Now you see us, and that's a start.
Thank you, everybody, for joining us here for our April public event for the Royal Astronomical Society of Canada Montreal Centre. We are really excited to have with us today our keynote speaker, Dr. Laurie Rousseau-Nepton, who is the first female Indigenous astrophysicist from Canada. She's working at the Canada-France-Hawaii Telescope. And before we get to her, we like doing a few welcomes here at the Montreal Centre. We typically start with a land and sky acknowledgement. So rather than just doing an acknowledgement of the land and acknowledging that we are on unceded lands, as astronomers, we also recognize that we are on shared skies. So those of you who went to the next door area for refreshments or are looking here around the room, you'll see some of the Indigenous constellations, which we acknowledge, and we also learn the stories of these because we share them in the night sky with all of the traditional Greek or Roman constellations. We also look at the lunar month and we try to identify the way in which the First Nations saw the lunar month. And we are currently ending the birds laying eggs moon month, according to the Mi'kmaq on the East Coast. But most of us here kind of, I think, associate more with the Ojibwe and their view of the April moon as the maple sap boiling moon. And I know I've been seeing pictures of my friends here in the West Island boiling away their maple and telling me all the wonderful syrup that they have at the breakfast table and color me jealous. But we are also on our way to the next moon because this morning, this morning we had a waning crescent because we have the new moon coming up tonight. And that waning crescent moon was less than 5%. So we are going into the frogs croaking moon next, where we will be hearing the frogs singing the songs of spring through the evenings over the next few weeks. Now I'm saying that it's a new moon tonight, but that's actually something really important right now because when we have a new moon or a full moon, we have a chance for a solar or a lunar eclipse. And we have a solar eclipse happening tomorrow, but it's not going to be visible for us here in Montreal. This is the path of totality. And you can see it skirts through parts of Australia and the Southern Hemisphere. So they will get to see part of a total solar eclipse. Us here in Montreal, we're really excited because in October, we get to see a partial solar eclipse, and it's an annular solar eclipse. We're only going to get to see about a few percent of the sun covered by the moon. But in just under a year, on April 8th, 2024, we will have a total solar eclipse pass through John Abbott campus. So if we have clear skies, we will get to see the atmosphere, the corona of the sun with our own eyes safely. And we'll get to watch all of the stages of the eclipse throughout the afternoon and early evening hours on April 8th, if the skies work with us. Now, I have up here as well the annular solar eclipse from June 2021. And part of the reason I have that there is because that's the last one we got to really enjoy here together. It was during COVID times. And part of it was because this is where I first got to know some of Dr. Rousseau-Nepton's Inclusivity projects, because she did a video for us on the stories of the solar eclipse, and she did it in multiple languages. So we had that story in Innu, we had that story in English, we had that story in French. We were able to share that during our outreach events back in June of 2021. Now, before I go any further, I'm going to call on our honorary president who is joining us from Arizona, David Levy. He starts all of our public events with a literary reading and a welcome. So David, let me turn the floor over to you.
Thank you very, very much. I hope you can hear me.
Wonderful.
Thank you. I am really excited about listening to this talk. And so the quotation I'm about to read to you has no relation at all to what I'm expecting from the talk, but it has a lot of relation to why I and so many of us have caught the bug of being amateur astronomers loving the night sky. And this is going to be from Walt Whitman's famous poem, When I Heard the Learned Astronomer. I'm looking forward very much to hearing the learned astronomer today. And, but this is the poem. When I heard the learned astronomer, when the proofs, the figures were ranged in columns before me, when I was shown the charts and diagrams to add, divide, and measure them, when I, sitting, heard the astronomer where he lectured with much applause in the lecture room, how soon unaccountable I became tired and sick, till rising and gliding out, I wandered off by myself in the mystical moist night air, and from time to time looked up in perfect silence at the stars. Thank you. Good luck on your presentation. I need to run off for a few minutes, but I will be back. I'm going to catch most of it. Really looking forward to this. Back to you. Thank you.
Thank you so much, David. It's always a pleasure to have you join us. This is one of the benefits that we've had recently with COVID, is that David is able to join us for all of our public events. I'm now going to ask our Vice President of the Royal Astronomical Society's Montreal Center, Maury Portnoff, to give a few moments about what the Society is.
Thanks, Karim. Where's my friends up is Kuta was saying Karim. Hey, hello. I'm going to just mention a few things about RASC, or Royal Astronomical Society of Canada. There's two parts. There's the national part, and that's 150 years old. And we're the Montreal Center. There are centers right across Canada of over 20 centers. And once you're a member of one center, you're usually welcome in all the other centers. So it's a wonderful group to join. And there's astronomers at all levels, from really beginners to people like David, who's infamous for his achievements, and local members who are experts in astrophotography. And then there's other members like myself who just like to look up and enjoy the night sky and the day sky. We also like looking at the sun, but safely. And then you have RASC Montreal, which is our group here. We're mainly located at the Morgan Arboretum, but we have a wonderful relationship with McGill and John Abbott College. And because of that, okay, you do that. And because of that, we're lucky with John Abbott College to have a library, the I.K. Williamson Library, and access to this room and all the wonderful facilities. It has also given us a wonderful partnership with the college, with the students, who've given us a breath of youth and enthusiasm, which us older people sometimes lack, because we just get stuck in our old ways. So it's a wonderful relationship with John Abbott, and we're really happy to be here. So if you're new to astronomy and not a member of RASC, join us. It's going to be the best investment you can make in your astronomy career, and it goes on and on. Much better than spending money on an eyepiece or another telescope, because you'll do that anyways. But what you get from joining RASC is priceless, as they say. As upcoming events, our next public event is going to be next Saturday, I believe the 29th, right here in P204, Penfield 204. And we're going to have one of our members, David Schumann, there. He's our local space expert, and he's going to be giving a talk on space travel, not yourself going up in space, not yet anyways, but if you want to visit places in the States like Cape Canaveral, Kennedy Space Center, where to go to see space-related tourism sites, and what's your chance of seeing a launch and things like that. Now I'm going to give you a challenge, and then I'm going to sit down. If you're coming next Saturday, think of a question for David. Try to stump him. That's my challenge to you. I don't think you'll be able to. So again, thank you for being here.
Thanks, Maury. So what you're all here for, of course, is our main event for today, which is the Signals from Above the Clouds talk by Dr. Laurie Rousseau-Nepton. And I was trying to decide what was the best way to introduce her, and then I didn't end up having to think about it, because I was given a contact from Dawson of a young lady, Kayla, who volunteered to say a few words and introduce Laurie. So Kayla, can I turn the floor over to you?
Hi, can you hear me?
Yeah.
Hi, Laurie. Hi, everyone. I just wanted to say welcome and thank you for being able to present. I won't be able to stay very long because I have to go study for an astrophysics test, but you're very inspiring to me because I've been interested in astrophysics for a very long time, and you're the first Indigenous astrophysicist that I've ever seen. And it was a gift to get to attend your talk last year, I'm pretty sure. I'm not sure if I got to speak with you, but I got to hear your talk, and it was very inspirational with the knowledge that you gave us, and it was really a gift. And I hope everyone enjoys her talk today. I didn't really prepare much. I just wanted to say thank you, and you're very inspirational.
That's awesome.
Okay. You can watch it later.
All right. Okay.
Kayla, and yeah, it's very nice, and you're the very reason why I'm giving talks like this, to inspire you guys. So it's really nice to hear that it works. And I'm going to say Kwe, aloha, hi, bonjour, everybody. I'm very happy to be connected from very far away with you guys. It is just past 1 o'clock in the afternoon here in Hawaii, and I have prepared this talk for you. I'm going to show you a little bit my path, how I ended up here, some of my research, some of my side projects, and where I'm heading with all this. And I really like to have a conversation, although I'm on Zoom. If you have any questions during my talk, feel free to either pass them to Karim if you're in the big conference room, or just use the chat or the Q&A and the Zoom, and I'll try to keep an eye on it. Sometimes I get into talking too much and I don't notice there's a question, but I'll eventually get to it. Yeah, so I'm going to start sharing my screen right away, and in a few seconds, you'll be able to see my first slide. So, so the topic, signals, it's something that is very dear to me. It's my science project. It's an acronym. And we're going to get to this project at about midway. But before we get there, I wanted to share a little bit about my story, where I'm from, and so you guys have a better idea of who I am. And so I want to start with those pictures of my wonderland, the place that I love the most in the world. So if I'm on vacation, I'm likely over there. It's in the Astronomy Reserve, north from my community in northern Quebec. Although if you look at the map, it's not that very far north. But in my community, for the Innu community, who lives very close to Mastoyats or Pequot-Kamilnuats, it is further north. And so there's a camp there that my family has been using for hunting moose for generations, and I like to go there. Disconnected from the computer and the phone, but very connected to the land and the sky, which is a very special thing. And the Astronomy Reserve is actually an Innu word that means where we go wait for the moose. So it has a meaning in languages. Even though I don't speak Innu fluently, I know a lot of words, and I know enough to know how much languages are important. And even here in Hawaii, learning a little bit of Hawaiian, I know that they carry meaning that extend just the meaning of the words. And Astronomy is where I learned to be a good observer, to look around and look for signs, of course, to be a good hunter. Looks for signs of presence of moose, but also looking at the weather pattern, the sky, and all the things that influence the life on Earth, the animals, and even us. And I think that I've always been an astronomer without even knowing it. You know, when you're young, you don't know you can do astronomy. But now the more I think about it, the more it was obvious that I would end up being a scientist for sure. And a scientist studying the sky, yes, of course. I was asking a lot of questions and very inquisitive and looking around and being passionate about our environment. And so I was always the first to find things or find tracks and see things. And it's actually very important when you're hunting. But in science, being the first to observe something, to notice something, to study something is part of my job every day. And I do it here in Hawaii. So the land, the territory is very different. It's not something that I was familiar with. So on the big island of Hawaii, you have this gigantic mountain. There's two gigantic mountains, the Mauna Loa and Mauna Kea. And so you see them from very far away, wherever you are. And so it's very easy to know where you're at, like, because you see the mountain. In Canada, in the Shakmushwan Reserve, a lot of the forest is very similar, and you need to know your marks and know your path to find your way back to the camp. Here it's different. But I live here on the native land of the Hawaiian, and I use a telescope that is located on the summit of one of the most sacred mountains here, which also is the site of multiple cultural activity, and which has a meaning for the Hawaiian people. And they also have multiple sites on the island. Hawaiians were building really large structures that some of them were also used for astronomy. So I'm just showing you here a platform that is built in one of the cultural sites here. And we were actually there in March for the equinox. And we attended with some astronomers at the ceremony that is performed here by the Hawaiian, and what the equinox meant for them. And it was very beautiful. And so I need to acknowledge the site and the people that are here, because without the Mauna Kea, I wouldn't be able to do the science I'm doing today. But before ending up here, I started in Canada. So more modest sized mountain, the Mont Mégantic. So about 1 kilometer height. It's still a very nice site for astronomy. It's one of the dark sky reserve, and there is a science telescope there that has a mirror of 1.6 meter wide. And I could access it when I was a student, and I could learn what the telescope is capable of doing. I could also learn, to use it, but to perform all of the observation myself. And it was a unique experience because I learned from an astronomer working at Laval University, Carmel Robert, and she taught me a lot of things on site. And without that, I don't think I would have been able to qualify for a position like the one I'm holding today at the telescope, the Canada-France-Hawaii telescope. So learning on site with a professional was really, really a gift. And on top of that, my project was a project that involved instrumentation. And when I say instrumentation, it's about the kind of cameras we put behind the telescope to take data. So instrumentation in astronomy is a very vast domain, a very vast field of astronomy. But we were building a prototype, something that had never been built before, and it was called espion. And in French, espion means spy, so it was a cool name. So espion, the spy, was meant to be looking at the night sky in a different way and producing a lot of data and enabling an astronomer to do new science with it, because the data was just different and better and more extended. And so when I joined the team, when I started my master's, I studied physics. And then I just simply knocked at the door of Carmel Robert, that was my astronomy teacher back then. And I told her, I want to do a master. And she suggested to me, yes, she said, yes, of course, arm open. And she said, you could do a project with this prototype, Espion, and see if we could study galaxy with it. And more precisely, how stars are forming in galaxies. And so without necessarily being an expert in that, I jumped into the adventure and joined the team, spent a lot of time at the observatory, so much so that I became slowly but surely an expert in using Espion and analyzing data. And on this picture, actually, I'm right here, and I was training other students to use the telescope. So after just a couple of years, I could then just follow this cycle of training new students coming in. And it was very rewarding to be part of that team and of that cycle. So Espion, it's an acronym. It means spectroimaging at the Observatory of Mont Mégantic. So you might not be familiar with the term spectroimager. So you will by the end of this talk be. It's a very special kind of camera. And I was working there with camera, but it was developed by a team that was also working with Laurent Drissen at Laval. So Laurent Drissen is also Carmen's husband. And so we had a very large team of students and engineer working on the camera. And we were also part of a larger organization with multiple universities, and I was right there in the middle of that picture, but working with University of Montreal, University of Sherbrooke, Bishop. So all these universities kind of work together towards projects like these. And eventually, in a good sense, the story of Espion really worked well. And we got good data, and we were able to prove that the prototype was working and ready for science. And we got funding to build a bigger one, a better one, that would be installed on an even larger telescope, the Canada, France, Hawaii telescope. And that one is called CITEL. So CITEL is also a spectroimager, and it is here with me in Hawaii, and it is observing for people across the world. And it's a technology that was developed in Canada with a small team of students and engineers, and ended up here being used internationally now. And on this picture, you see Julie Mandar. She's an engineer. She was the engineer that was leading the project to build this new instrument, CITEL. And so I'm going to show you a little bit how it works and why is it so special, those spectroimager Espion and CITEL. And so I'm going to start by just showing you a periodic table, but a very different one. So, and on this periodic table, you see all of the elements, and well, most of them, not all of them, but you also see their spectral signature. So each element, when they are warmed up, and when they lose some electrons and they're ionized, they start to emit light when they collide with either electrons or light. And when they do so, they emit very specific colors. And it's like their fingerprint. It's like a way to identify them from very far away. So you can use a spectra or the color of those elements, those signature, these colors that comes from the sky and go into your instrument. And if you have a spectrograph, you have access to these colors, and you can see them and identify where what emitted that light, which atom emitted that light. So it's very powerful to be able to identify atoms from very far away. Especially if they're in space in another galaxy. So spectroscopy is important, but you also can use that spectroscopy in different ways. So here's just an image showing like different configuration. Like if you're observing, like let's just pick this telescope on top. If you're observing a star directly, there's nothing in between you and the star, you'll see basically a spectra of all the colors emitted by that star. Which is basically a rainbow. And if the star is a little bit more red or a little bit more blue, you might see a little bit more red or a little bit more blue in your rainbow. But then you have other configuration because space is filled with stuff, including a lot of gas. And so most of the time there's gas in between you, the telescope, and the source of light. And the gas itself can also emit light. So if you have a configuration like this one here, where you have a telescope pointing towards some gas and there's a star behind it, then the spectrum of your stars will start to have like dark areas. And most stars do, because they have atmosphere, like clouds, and some have clouds, but some have just like hot atmosphere. And then you see those kind of weird signature that also come from the atoms in the atmosphere of your star, but they're dark. They're kind of inverted. So the light is absorbed by those atoms in very specific colors, and you can identify them. And then if you're just looking at the gas, which is sometimes warmed up, then it starts to emit those different colors, and you can identify them. And you have like an emission line spectrum like this one here, where you have like nitrogen or oxygen or hydrogen, all of these atoms shining in your telescope. So spectroscopy is cool. You can see all these stars with different kind of signatures, and the gas with different signature as well. So being able to build an instrument capable of splitting the light in all the colors of the rainbow gives you a lot of information that you don't necessarily have with just one image. But an image is important. So CITEL and Espion are kind of doing both. They produce images, and for each pixel of your image, you have a rainbow or a spectrum of your pixel of what is in that object in that position. So Sutel was built, developed, and thought to be very performant, but it had to be working at the summit of the Mauna Kea. So at the end of my PhD, I was testing the instrument in a small, well, in a very gigantic refrigerator that was borrowed by, and that was used from the Department of Civil Engineering at Laval University. So we kind of arranged something with the Civil Engineering Department so that we could put Sutel, the whole instrument, in one of those big refrigerators that are usually used by them, I think, to test beam for bridge or like construction of large buildings. But the good thing is that you can lower down the temperature up to minus 20 degrees C if you want. And that's what we wanted. We wanted to see how the instrument would behave in very cold temperature, like it is at the summit of the mountain here. And so I was working with the instrument for a couple of weeks in those extreme environment, testing it, adjusting it, and then we shipped it to a plane to Hawaii for what we call the first light. So that's when the instrument is going to get, for the first time, light coming from the sky. And there was a scary hurricane coming towards the island at that time, and we thought that we would all lose our time to bad weather. But for some very fortunate reason, the hurricane decided to go north, and that's a big island in the islands of Hawaii. And the hurricane just like went completely sideways, and we got 7 nights of perfect weather. And we observed our first target that was a beautiful nebulae that we call a planetary nebulae. And that's the color image of it. It's close in our galaxy. It's a star that is like not super big, but that has ended its life and has kind of ejected material. But what I was interested in was the background galaxy. So there's a tiny galaxy there. And in the background here, that's what I was doing, analyzing the data and trying to extract information from the spectra of the galaxies. And so for every pixel of that image, there's millions of pixels. We had a spectra, and those spectra contain information that I could use to extract, for instance, what we call a velocity curve. So that galaxy is rotating on itself. And if the signature of the atoms are kind of shifted towards the blue or the red, it tells me if it's coming towards us or away from us. And I can build like a velocity image, like how the galaxy is actually moving. And then I can also identify some atoms from different origin, like oxygen and hydrogen here. And we can make a map of how much oxygen there is compared to hydrogen. It's a very common thing that we do in astronomy because hydrogen is like the easiest, simplest atom that was there after the Big Bang. And so all the heavier atoms are produced by stars and other phenomenon, or most of them. And so if you see a lot of oxygen, like in the center of the galaxy, well, it's because there's many stars that are contributed in kind of enriching the universe with those new elements. And so you can see this phenomenon happening by looking at a map like this of how much oxygen there is. So I, very soon after that, finished my PhD, defended my thesis, very stressful period of time. And this is a picture of me with the cohort of PhD students. So you have my supervisor, Carmen Robert, and the other students that were all coming from other countries. So from France, and then from Morocco and Burkina Faso. And it was a really nice team that worked on different projects. So there was another student, Thomas, in the back here, that was also working with Sutel with me. And so I moved from Wendake, which is the place where I was living nearby Quebec, to Hawaii just after that. So got a visa, took all my stuff and my 2 cats, and boarded a plane to move here and start my first job on the Big Island. This is the Big Island. If you're not familiar with it, it is a very special place. It is located in the middle of the Pacific Ocean, so you're very far away from everything. But it is also a volcanic, active volcanic island. And what I like about this image here is that you can see the Mauna Loa, which is an active volcano with its multiple lava flows. Those are not rivers, they're older lava flows that emerge from the main active area of the volcano. And you can also see the Kilauea, another active volcano in the south, and the smoke coming out of the crater of it right there. But fortunately, I work in the northern part, so that's currently where I am right now. And the Mauna Kea here is also in a quiet area, and Mauna Kea is a sleeping volcano, has not been active in more than 10,000 years. So volcanoes also equal earthquakes, constant vibration, which is not necessarily something easy to work with in astronomy. We work with those instruments that are very sensitive to vibration, actually. Sutel is very sensitive to vibration. You'll see why a little bit later. But we work with it, and we manage to get extremely good data, even in those conditions. So we're far away from the volcano. Even the summit of the Mauna Kea is a couple of, at least 2 hours of drive away from the Kilauea. And this is a picture of the Kilauea crater in 2021. That's an eruption from the Mauna Loa in December. That one was closer to the telescope. It only lasted a week, but during that week, the sky was so bright that we couldn't conduct a lot of observation from the Mauna Kea. It was blocked a lot by the light pollution from the volcano. And that's a more recent picture of the lava lake and the Kilauea. And the Mauna Kea is a very special site. So this is a picture of the Mauna Kea in the winter. It's very special for astronomy for many reasons. And I like this picture because, first of all, we can see, well, there's snow in the winter, but we can see the clouds that are most of the time below the summit. So driving up, you'd have to cross the clouds. And this is what we call the inversion layer. So this inversion layer is usually there, but it can sometimes be higher. And then we have bad weather, but 75% of the year, which is a good statistic, we have good and clear sky at the summit, which is a unique aspect of it. But then there's also a couple of other things that make the Mauna Kea very special. So we're in the middle of the Pacific Ocean, and over here, there's what we call the trade winds. So there are winds coming from the east to the west most of the time, which makes one side of the island the wet side and the other side the dry side. So the humid air coming from the Pacific Ocean comes and get compressed by the presence of these gigantic mountains, and then the water all falls, all the rain falls in one side. And then when it reached the other side, it expands again. And so the water doesn't condensate. So we have one wet side, one dry side. And those winds are constant, and they're not perturbated by any structure, other structure, or other like geographical features, mountains, hills, because it's the flat ocean. And so you don't necessarily have this turbulence pattern that would naturally happen when air is flowing across the land in Canada or on the mainland. And so the air is what we call a laminar flow. It flows and it is not doing those turbulence pattern because of any structures. And this constant flow of air that is super flat reached the summit. And of course, after the summit, it gets like some turbulence, but at the summit itself, it is flat. And so the telescope are observing through that, and it makes the stars looking very pointy and very, they basically don't twinkle too much. And that's something good. No twinkling is good in astronomy. We want to detect things that are sometimes very faint and very far away. And if their light is moving around and spread over many areas of our camera, we don't detect them as easily. So having those pointy stars not affected by turbulence is great. So that's unique of being in the middle of the Pacific Ocean. And then as a kind of a side benefit from having those clouds forming, especially on, they form naturally on the two main cities. So Hilo and Kona are often covered by clouds, especially in the afternoon, and often a large portion of the night. So these clouds are kind of blocking the light pollution, keeping it down below and keeping our sky very dark. So that's another special aspect of here. So this is another view of the mountain from a scene from the Mauna Loa in the summer. And now we're seeing a bird view of at the summit. And then if we look closer at the area on top, this is not the real summit. The real summit would be over there. This is the science reserve with all of the telescopes. And the Canada France is this one at the very end of the road. And it is located at, to my opinion, the best spot on the mountain. And now this is a picture from the summit. This is the Canada France Hawaii telescope, and you have other telescope all busy observing with different cameras that have different features that enables different science, from observing stars to exoplanet, galaxies, faraway universe. There's a lot of option up there. And so if we get closer to our telescope and we jump inside the building, from up top, we would see the telescope, which take most of the space in the dome. And right now the mirror is covered with the rose that protects it during the day. But I'm going to show you a video that shows the mirror. And this is, again, the telescope with one of my colleagues right beside it, just so you have an idea of how big it is. And that's my little video. So you have an idea of what it looks like. Being in the building when everything happens is very special. It's a very big environment. The telescope itself is a huge piece of equipment and everything can move. So this is the dome slit opening just about the time of sunset or just a little bit before it. We want to keep the whole environment cold to avoid turbulence. So if the air was warm inside the dome, it would then start to go up and make those turbulence that we don't want to have above the telescope. And then the dome can rotate and the telescope can point in all directions. And we have little windows also that helps the air coming in. So everything is kept at about the same temperature as outside. And we have a whole team that maintains the building to make sure everything works. And right now it's tilting towards us. I'm going to pause it right there so we can see the mirror. Our primary mirror, the main mirror of the telescope, is 3.6 meter wide. It is in the shape of a donut. There's like a hole here in the center. And then we have different instruments. We have 5 of them. CITEL is one. But we have 2 cameras that can be installed on up top. And one is observing the visible light. One we can see with our eyes. The other one is looking in the infrared. And we have at the bottom of the telescope 3 spectrograph, high resolution spectrograph that are looking at stars, and the visible and the infrared, and CITEL, which is an imager that doesn't look at one star at a time, but at a large field of view as big as the moon almost. And so when we are observing with spectrograph, we do put another mirror here, the secondary mirror. So the light comes in from the sky, hits the primary mirror, focused into this smaller one, the secondary mirror, and then is sent back into the hole of the donut, and then sent into the camera, the instrument that is located below. And so this is me pushing CITEL before it is installed on the telescope. And this is CITEL once installed at the bottom of the telescope with all the electronics and things that make it work. And I'm not doing that alone. Actually, I'm rarely at the summit when this happened. We have a whole team of engineer and operational staff that helps us connect the instrument and do the testing. So this is part of our team. And yeah, that's how it works. So now I'm going to enter another phase of the talk where I'm just going to introduce to you a little bit of the concept regarding my science, star formation, that leads us to Signal, the large program that I am leading nowadays. So we don't jump into the universe, into star formation right away. We need a little bit of background, and I always like to talk about things from the beginning, or not necessarily the beginning. We don't know if it's a beginning, but we call it the Big Bang. So the moment when our universe started to change drastically and started expanding. So 13.7 billion years ago, our universe was like a soup of particle and light. It was something completely different than what we know about it today. And for some reason, it started expanding, and there are multiple theories about the reason for that. But as a result, in its expansion, the energy that it contained is something that is fixed, and it started to dilute, and those little soup of particle and energy and light started to form object structures. And so at that point, the universe was kind of simple, but it became more organized and complex and formed galaxies and stars. And that's mainly because of the force of gravity. So gravity is that force that we can't see that enables matter to be attracted by other particles. So each particles have a mass, can be attracted by another particles which have a mass. And so there are people in astronomy working on those beautiful simulations. This is not my work. This is the Millennium simulation. It shows the evolution of our universe since that time. And with time, we see those filamentary structure, kind of looking a bit like a sponge. And you have areas where you have a lot of galaxies, clusters of galaxies, and void where you have less matter. And so, so that's what time made to our universe in combination with gravity. And within those galaxies that, believe me, at the very beginning of the universe were really small, you also were forming the first stars. So those stars formed slowly because of gravity, collapsing particles were just collapsing on each other. And then at some point, the object at the center get massive enough so that something very special happens. There is nuclear fusion in the heart of the star. So that happens because there's so much pressure from the gravity of the object that the center, the atoms at its very core, in its heart, gets close enough so that these nuclear fusion can happen. Nuclear fusion means atoms becoming larger, fabricating heavier atoms, but also means producing a lot of light. So that's when the star light up and produce so much light. And will do so for a very long period of time, which depends on its mass. So if you have a star like the sun, it will take billions of years burning the elements in its core. If it's a more massive star, it can be a little bit faster because they are much heavier and they compress their heart more efficiently. So while those stars are forming in our tiny galaxies, galaxies continue to grow, and they grow mainly by absorbing gas around them and by merging with other smaller galaxies. And so this simulation here shows how those galaxies merge, and it's again mainly due to the force of gravity. And this simulation, this kind of green is the clouds of gas, mainly hydrogen and helium, a little bit of lithium from the beginning of our universe. And then stars are forming in blue. And so you see these blips of star formation everywhere where there's a lot of gas in galaxies. And then what is red is, as it goes, the older stars, the stars that are older tend to be a little bit smaller mass and more red. And now we have a galaxy, a spiral galaxy that kind of look a little bit like our own, like the Milky Way. Everything goes fast in that simulation. Just to give you an idea, for one turn of this galaxy, it's about 250 million years spent in this simulation. So every turn is a lot of time, and stars are forming at a very fast pace with respect to that. Only a couple of million years to form stars in a cloud of gas, and they can be there for a while. So that's an artistic rendering of what those first galaxies, the small ones, might look like. And they contain the first stars, which were formed out of the gas and the material of the early universe, so mainly hydrogen and helium. And they were different than the stars we know today. Most research about those first stars know that they found clues that show that they were more massive, or at least enabling the formation of stars that are really, really massive, like 1,000 times more massive than the sun, which is not something that happened yet, that happens still today, because our universe that transformed, and it got transformed by those first stars that produce a lot of heavier atoms. And so the composition, the chemical composition of the universe changed, and we're not forming similar stars. Stars like the sun are definitely enriched by a lot of material from those first generations of stars. If we look in the faraway universe with telescopes, with Hubble, for instance, we see all these galaxies. There's like billions of them. at different distances. They have different shape. Some of them form a lot of stars. Some of them are more passive, more quiet. They don't form as many stars. And there's reason for that. If we look at the classification of like the shape of galaxies you might find, so this is a typical Hubble classification scheme where you have some very massive elliptical, like kind of egg-shaped galaxies with a lot of old stars. And on the other end, you have spirals that do form a lot of stars. Sometimes they have a bar, sometimes they don't, and sometimes they are smaller and irregular with no like specific shape. And those irregular are actually looking a little bit more like the galaxies of the early universe. So they can be studied in that way to understand how galaxies first started. So that's some very common spiral and bared galaxy that we know in the surrounding of the Milky Way, and that's one of the Magellanic Cloud, which is an irregular galaxy. And sometimes you have some that just don't lie in that scheme with a ring that can be produced during collisions of galaxies. Okay, so I'm studying star formation. So when I look at a galaxy like this, what I am interested in is those red blobs. So those red blobs are star forming regions, area where new stars are forming in gas. And why do I know that? It's because those red clumps are warm gas that is warmed by the presence of very massive stars. And you might remember I mentioned massive stars don't live very long. So when they're big, like 10 times, 100 times the mass of the sun, they burn their fuel very quickly. They produce a lot of very energetic light. And this energetic light is nothing compared to what the sun can produce or a smaller star. So this light is so energetic, it goes around and create a bubble of plasma, of warm gas. And that warm gas starts to emit light itself, like the signature that I showed you in the first periodic table, those little atom signature. And they start to shine in a very specific color and a lot of red for the hydrogen, and there's a lot of hydrogen. So I see those blobs of plasma, hot gas, emitting a lot of red. I know it's mostly likely star formation. And that's what I'm interested in. So if we focus on an area like that in a galaxy, other teams are simulating. This is a simulation from a team in the UK. So this is a cloud of gas in a galaxy. We're going to let it evolve with the force of gravity and other kind of perturbation that helps the gas to condensate. And in this video, those yellowish filaments are like getting denser and denser, and then eventually fabricating objects that will light up eventually, get the mass that they need to be able to light up and start to do nuclear fusion in their heart. And out of a cloud of gas like that, you will form 10, 100, thousands of stars that are like sisters because they are fabricated out of the same material. But even though they are sisters, they are very different. Some of them are small, some of them are like the sun, and some of them are massive stars. And the beauty of that is that we can compare what those simulations are saying with normal observation of like newly formed stars. And we do see those clusters of young stars with their warm gas around them. And we do see that only a few of them are massive, and in some cases very massive. Like this is another simulation showing like very massive star production. And this is a comparison with like a region that contains very, very massive stars for our local time, which is about like 150 times the mass of the sun. So that's very, very massive. And so only a few massive stars for a lot of stars like the sun or smaller. And that's a very puzzling scheme, because if you look at different areas of galaxy, wherever the stars are forming, you'll always have the same ratio of those very few massive stars with respect to those numerous smaller mass stars. And this is what in astronomy we call the stellar initial mass function. And it's thought to be kind of stable, but other projects like Signals are trying to figure out if that's the case, if it's everywhere the same, everywhere you are in the universe, if all the massive stars are forming in the same amount. And why that is so important for our understanding of the universe. And this is why I'm going to show you this second periodic table. And I like this one because the colors here of the elements are showing you where they are coming from what kind of mechanism in our universe those elements are fabricated. And so massive stars are in green here. So those massive stars, they don't live long. And at the end of their life, they're going to explode in a supernovae. And that's a very cataclysmic event, and it pushes a lot of the material that they fabricated in their life elsewhere in the galaxy they live in. And they contribute a lot in changing the chemical composition of a galaxy by shooting out those heavier elements. And so if you look at all these elements in green, they are mostly fabricated by supernovae explosion. And they are so important, and the reason why we have planetary system like the solar system and planets like the Earth, and even whatever you find on the Earth. So understanding this mechanism, the massive stars, is very important, and their number when the stars are forming is also exclusively important to understand the evolution of the universe. So they form in small number, but they're still there. And when they do, they start to shine, and the light is starting to warm up the gas around them. And so here you see, we don't see the stars at the center of this simulation, but it's like a 10 solar mass, so a star that is about 10 times the sun mass. When it lights up, it creates a gigantic plasma bubble. If it's larger, it will create a larger bubble, and it will create it faster. And that's what I study, these gigantic bubble of warm gas that we can see from far away. And that's a comparison with a real observation of these bubble that we always do when we simulate things on our computer. We always compare with real objects like this one here and there. And it's a cycle. Just like things that live on Earth, stars are basically born in an environment that is different than the environment that they will be dying, and they will affect that environment. If it's a supernovae, a massive star, it will transform its environment by enriching it with its new material that it's fabricated in its heart. And so the next generation of stars that are there are going to be formed out of that new material and be different. And this evolved through the age of our universe. Each generations of stars are affected by their previous generations and are different. And we are trying to study those characteristics and to study how this phenomenon it changes as the universe is aging. And to do that, we need to understand our past, but also try to forecast our future in our universe. And so to study those regions, I have in hand multiple kind of tools or ingredients in my recipe to kind of figure out how they work. So you have the stars and the gas, and how the physics inside those regions works. To understand it, you really need to consider a lot of things. So as an astronomer, I study the stars, the massive stars. The O and B stars are the most massive one, are in there. They produce the most amount of light. So I need to know their light spectrum, what kind of light is sent into the gas. I need to know the gas density, the gas abundances, what are the elements present in the gas. And then ultimately, what we call the free electrons. So as light interact with the gas particles, there's electrons that are kicked out of their atoms, and that becomes a population of free electrons, and they are responsible for colliding with other atoms and also recombining with them. And that's actually why each atoms produce specific colors of light. Those transition and collision with electrons are the reason why we have those signature of light. So it's very important. And this phenomenon happened quickly and lasts a couple of million years once it's there. So the plasma bubble will live on for a little bit of time, and I'll be able to observe those colors coming from the gas for a few million years and study it. But studying one region is good. Studying hundreds is better. Studying thousands of regions is even better. Because it happens very quickly in different environmental galaxies from the center to the outskirt. And that's a quick video that shows how those bubbles of plasma kind of light up and die off as supernova explodes and things like that. And one other thing that is important is the scale of star formation. So we on Earth are not necessarily familiar with those astronomical scales. So you might have seen before this beautiful image of the Orion Nebula. It's a very popular one. I personally had it on my desktop back image for a very long time. And this is actually a star forming region. You see the big bubble of plasma and the warm star right there. And it is actually a super small region. It's just close by. It's so close to us that we see it like a gigantic nebulae. But it's very small. In astronomy, we use the parsec as a distance measure to measure distances and sizes. And this is 4 parsec. It's very small. We go at a little bit farther away in the universe. So we are leaving the Milky Way to another smaller galaxy that contains a lot of little regions where stars are forming. Some are 25 times bigger than Orion. Just right there, you have this gigantic bubble there. And other smaller ones with smaller clumps. But remember that one. It's a good example of like this perfect spherical H2 like star forming region with warm gas. And now we're going to go farther away to other galaxies that are much farther at millions of parsec distances, where we have like areas that form stars that are like more than 200 times bigger than Orion. And here's our a region that would be comparable to our big bubble there. Same for this galaxy even further away. And I like this galaxy. It's my favorite one. It's NGC 628. It's a perfect spiral. It contains thousands of regions of star formation. And if we focus on those areas, I have a little code that identify a star forming region and kind of spot them in a map. And we can even zoom in into a smaller area where we see a bunch of them. And now this little area that might contain just a few pixels of my image is just as big as this 100 parsec region, or 250 times larger than Orion. So it just put things into perspective. In the universe, there are really, really large area of galaxies that are forming stars. And as you move out and try to observe things in galaxies farther away, well, things like Orion they're basically non-detected because they're too small. And very large region containing lots of stars and lots of gas are just a few pixels in size. So studying the nearby universe gives you a hand on things because you can see what happens. And as you move farther out, you lose a lot of information. And you lose a lot of information that is important to study those really complex systems that form stars. And to add on to the complexity of studying them, they swim in an environment full of stars and dust. And there's also emission from gas coming from diffuse area that kind of blur a little bit your data. And you need to include all of that to study the physics of things. And stars are not forming in perfect spherical shape all of the time. Sometimes they have clouds that are denser, which have different shape and temperature, and they're mixed together. And then your telescope will be looking into that, and you can have different kinds of stars, and your telescope's going to be looking into that from different angle of view, going through thick clouds or going through different kinds of things. So it can be a little bit challenging. But with CITEL, we have a very magnificent tool to do that, because you have images and you have spectroscopy, you have pixels. For each pixel of your image, you have lots of information about the light. And so this instrument is there to help you. And that's a couple of pictures of CITEL again. And if you dive into it, it's a very beautiful system that I'm going to try to kind of to explain to you in the most simple way. But what it does, and what is very special about CITEL, is that the center part, the heart of the instrument, the beam splitter, And you will notice there's 2 cameras in one instrument. And I'll show you a little bit how it works. But some of you might be familiar with interferometers, some might not. If you're not, that's fine. I have this very quick video that shows how it works. So you can imagine the light coming from the telescope, the source here, going into the instrument. And this is the beam splitter, the important part in the instrument. And it splits the light. Its name is very well chosen. So half of the light goes through, is transmitted, and half of the light is reflected. And on both arms of the instrument, either the upper or the left arm, there's a mirror. One is fixed, this one doesn't move, and this one can move. And it's very important because by moving this mirror back and forth, you actually change the length of the arm. So this arm will be shorter or longer than this arm. So what happens when you move that mirror, you'll change the path of the light. So light is split in 2 equal components, goes into the moving mirror, comes back, and is shifted in phase. So you'll notice that the pattern, the little waves from the light is shifted. And now it is shifted in a way that the waves cancel out each other. It's called destructive interference. So instead of measuring light, you measure nothing. It would be dark. And if you move again your mirror, you might move again those little waves and then put them back in phase. And then you'll see a bigger wave or a lot of light on your detector. And it actually looks like this here. This is an example of when you move a mirror and the interference pattern that are produced. So you have either bright fringes or dark fringes. So that's what it is inside CITEL. And the power of an interferometer is that for a light, like a laser, like a red laser, goes in the instrument, you can measure those interference. If the light of the laser is another color, like green, then the interference would look different because the wavelength is shorter. And your signal can be anything. It can be a combination of things, and you can measure those interference pattern. And then on the computer, as an astronomer, I just analyze those results, and I can get back what light actually is responsible for those signals. For me, mathematically, they are equivalent. Either I have the beautiful light colors from the rainbow, or I have these interference fringes. Mathematically, they contain the same amount of information, and I can get back the colors that are responsible for them. And that's just an example here of those beating patterns that can look very fuzzy and confusing. But with years looking at them coming from CITEL, believe me, they make a lot of sense. So this is an example. If you have 2 colors that are responsible for the signal, if you have 3, you start to have more beatings. And if you had 5 colors, then you have even more beating into the interference pattern. And that's beautiful. It's really beautiful data. And on top of that, CITEL is fine-tuned to get all of the light coming from the sky. So with this kind of like arrangement, maybe some of you had noticed that some of the light would go back into the sky after being reflected by the mirror. Some of them would go through the beam splitter and then be reflected. And in astronomy, we cannot afford light to be lost into the sky after doing so much work to capture it. So CITEL is tilted on the side, so we can have basically the 2 mirror, and then we have actually 2 detectors that collect all of the light. Which that means that we are kind of looking offset of the interference patterns. It looks like this when we look at the laser with CITEL. I have a video here that shows some of the data taken as we move the mirror, and you can see those beautiful interference pattern that might not look really friendly, but they are really, really nice, because to achieve this, the instrument has to be built in a very solid way. It is sensitive to vibration, so we have to correct for vibrations. And so it's a very sensitive instrument. And doing that, so by taking those interferograms, those interference pattern, we are able to build the spectra of the light and find out which colors are coming from the element that we're looking at in a galaxy. And with more images, more information on one side, we also get more information in the spectra, and we can see very defined emission coming from atoms kind of appearing in the data. So it's a very powerful instrument. And on a galaxy, because we can do that for every pixel of a detector, it looks like this. So this is a video showing the colors coming from that galaxy. And as I move into the color, you can see signals coming from hydrogen, nitrogen, sulfur. And I have a lot of things in hand to study the star-forming region's gas that is emitting that light. And that's what it looks like on the computer. For each pixel, I would have like signature like this, from oxygen, from nitrogen, sulfur, helium, and so on. So a lot of information also about dynamic, how galaxy moves and rotates, and additional things like that. And yeah, so let me check very quickly my timing. So I've been talking a lot, and I want to make sure I have enough time to show you. Yes. So Signals is my main project. And by now you should understand the acronym. So it means star formation, ionized gas or warm gas, and nebular abundances legacy survey. And I just noticed I have questions in here. Oh no, okay, it's just comments, perfect. So basically the acronym is meant to be the survey that studies star formation in all possible environment in galaxies. So maybe stars that are formed in the center of galaxy where there's a lot of other stars that are formed in the outskirt in an environment that is more less dense and intense, and other that forms really massive stars or much lower mass stars, and some that are very close to each other, like over there here in a spiral arm. So the survey is meant to capture all of these to understand them in a global way. What affects stars' formation and what affects their characteristics once they are formed in their environment. And we do that with close by galaxies so that we can see them in great details instead of losing the information while looking at galaxies farther away. And the reason for that is because we would be losing information as we would move out into very far away galaxies that are just a few pixels on a detector, like those higher, we call them higher redshift galaxy, because they look red when they're so far away. That would be similar to the galaxies that were formed in the early universe. So those galaxies are very interesting, even though we are not looking at them with signals, because when you look at a galaxy far away, the time it took for the light to get to us is millions, billions of years. So a galaxy like this was formed billions of environment where our universe was younger and completely different. So ultimately, signals also want to help scientists that look at those galaxies without much information and help them forecast what kind of star formation is happening in their galaxy. If I look at nearby objects that have the same characteristics, what kinds of stars are forming and so on. So the data look like data cubes. That's why I can make videos out of them. I can go through a data cube like this. So for every pixel, I have like the emission of the light in one axis, the spectral axis. So it's very convenient, and I can target different colors to kind of improve and optimize my data. And that's a video of a galaxy with signals, a nearby galaxy. It's a section of a galaxy, actually. And as we go through nitrogen, we see some emission, and we're going to go through hydrogen very soon. And we see the gas starting to light up when we reach those element colors. Same if we look at one tiny region, if I zoom in into the image, I can look at one star forming region at a time. And I can even see the signature of the velocities. There's a lot of things happening. The region is expanding, it has multiple filaments, and I can see that through the data. And the survey is targeting 50,000 of them. So that's just half of the survey here, and that's just the emission from the hydrogen atom. But it gives you an idea of what it looked like. And we have multiple softwares that are developed to study them automatically. And I'm doing this with a group of 70 researchers across the world. I'm not alone in this, but I'm leading the team. And I kind of want to conclude this, presentation by just saying that for me, I remember when I was a student, and let me just stop the sharing for a second. So when I was a student, I had no idea what I was going to do for as a research project. And it kind of, I followed a path, just following my intuition. I started to study at Mauna Kea Observatory and was ended this project with Espion, and I found out I really like doing instrumentation in astronomy, and both doing science and instruments, like building instruments for science, and doing both at the same time really was something that was good for me. And then as I was developing my expertise with observing with telescope and in the instrument, I was offered a position here. And also, as I had a lot of expertise, I could think about projects that could be done with CITEL, knowing how the instrument works and what are the latest knowledge available about star formation in our universe. I knew we could push that knowledge further using the camera. So that's how CITEL was, signal came up. I wrote the project and it got accepted. So it was evaluated and accepted as a very valid and valuable project to pursue. And so for me, it's just a natural flow. But when you're a student, you don't know all of this yet. It can be scary. You don't necessarily trust your ability because you're just starting, and it's normal. And it's just with time that you end up with that expertise, this kind of intuition that helps you figuring out what you're going to study and what science you're going to do. And so if you like science and you jump into that adventure just like I did, don't be worried about that. It will just naturally take its place, and you're going to find out where your place is into all of this. And now I'm transitioning from my position at the Canada-France-Hawaii Telescope to the University of Toronto and the Dunlap Institute for Astronomy. I will be starting there in September. I'll have a low teaching load. I have one class a year, and I'll be developing an instrumentation lab there, developing new cameras for telescopes that will include new technologies, and also technologies that I've used before with CITEL, those interferograms, those interferometers. And I'm going to combine them with the new technology available to build something even more powerful and more valuable for science. And I would have had no idea I could do that 5 years ago. So, so it's just to give you an idea of my thought process into this, and you might end up following the same kind of thought process. There's a lot of uncertainties, but it always takes its place. And as I will be teaching in Toronto and having students, I would love to have new students coming in and working with me. So I hope some of you might be interested and will contact me later on. But just to give you an idea, I'll be working with special detectors that are called microwave kinetic inductance detector. They are quantum detectors that work at very low temperature. This is a picture showing the detectors in a cryogenic system. And they are magnificent and fantastic because they also detect the light energy, which is a new feature that I will add to a new instrument building with the CITEL technology. And if we zoom in into those magnificent detectors, they have very, very small little circuit in them that enables to do that. So a lot of electronics associated with them and the development of this instrument. You will probably see me on the screen and starting in September. So I've participated in a project with the National Film Board of Canada, a documentary on the life of a scientist, like what do you do for your living, but also trying to make it more human because scientists are not, there's a lot of different profiles of scientists across the planet. And so if you feel like you're different than scientists, but you like science, it's probably because you haven't seen that documentary yet. So I hope you're going to watch it and enjoy it. The team came here in Hawaii to do some filming as I was training an intern. And also they even came with me hunting to talk about some of the aspect of ancestral knowledge in astronomy. And so I hope you guys enjoy it. And I have other science project that try to put some light or highlight the knowledge in astronomy in multiple communities across the world. So there's the One Sky project. If you know a good planetarium nearby that would like to project those short films that are showing cultural astronomy constellations and tools, developing tools for astronomy. They are available for free on our website, and they're absolutely beautiful. So feel free to go check it out. And as it was mentioned a little bit earlier in the introduction, I also participate in trying to share those stories coming from my communities, but others across Canada, trying to highlight how much knowledge was already there in our communities. And I always say, you know, back in those days, everybody was an astronomer. You needed to know the sky to do your daytime and nighttime activity. And so I think it's something very important that we highlight those and teach those. So feel free to go check them out. And the eclipse was already mentioned, so I'm just going to conclude by saying that there's a lot of opportunity to do projects in astronomy, even as at any stage of your training, whether it's high school, cégep, university, graduate school. You can always try it and contact an astronomer and try to see what kind of project you can do with them. I've been working here with students with all level, and I've always had fun developing project with them for them. And I'm going to stop there and take any questions you might have. Tanish Kumitin.
That was absolutely wonderful, Laurie. Thank you so much. We will start with a question online. There's a question from Michael Finkelstein. Assuming one is looking at galaxies billions of years old, where these galaxies are closer to the origin point of the Big Bang, how can it be no matter what direction one is facing, one is always pointing to the center? Is the origin point in all directions?
Yeah, so thanks for that question. Okay, it's hard to explain, but I'll try to do my best. You know, we are living on a planet in 3 dimensions. Our brain is made to understand things in those 3 spatial dimensions that we live in. And so there's mathematically, when you try to understand our universe and how it works, there is different topology of the universe. So the way we explain the spatial dimension in our universe. And one of the model that I like that is kind of helping to see why people are saying that wherever you point, you're kind of pointing in the same direction, is the Thor model, or the donut. So if you imagine a sphere, like we live in this planet, this perfect sphere, if we point our telescope in any direction from the Earth, you're able to look in all directions and everywhere in the universe. So imagine that this plane where you're looking at is just a circle. So all of these positions that you can look in all directions are within this circle, like a world map or a sky map, okay? So this is your sky map. It's a circle. And everywhere you look in that sky map, you're looking at all the position possible. So now you have a donut. So the sky map is like kind of looking at itself from the back. So that would be the topology. So if you would follow a light path for infinity in our universe, if the topology of the universe is correct and is defined by a Thor, then you would look at the back of your head X billion years ago, the size of the universe. We don't know what size of the universe, so eventually you'd end up looking there. The problem is we've never looked that far because of the size of our universe and the age of our universe. So the time the light can travel that distance. So that's the theory. Is it true? Is it false? That's up to questions. People have other models that explain our shape of the universe. So I wouldn't necessarily put my both hands on it, but it's one of the explanations.
I like that explanation because it means if I look far enough, I can see back when I used to have a full head of hair at the back.
Yeah, and you can see the Earth again, like basically wherever you would look at, if you look far enough or long enough, you'd see the Earth, or the area where the Earth is X time ago, where there would probably be just dust and particles.
Any questions from the in-person audience?
What does PC stand for in distance?
The parsecs, can you explain what they are?
Yeah, the parsec, yes. So parsec is a unit in astronomy because we're talking about such large distances that using kilometers is really not convenient. So a parsec is 3.26 light year, I think, I hope I'm correct. And a light year is the time the light, like the distance crossed by the light in a year. So, so as light goes 300,000 kilometers per second, you can do the math. There's X number of seconds per year. So you multiply these two numbers and then you get 1 light year, which I think, if I'm correct, it's 10 exposed 15 kilometers, more or less. And then the parsec is 3.26 times that. So even more, 10 to the 16th kilometer or something like that. So it's very large numbers.
We've got a question from Carl asking, is using gravitational lensing a possibility for Sibel in the future?
Yes, it is. So the beauty of gravitational lens is that they enables you to look at objects that are very far, even farther away. So basically you have the lens. The lens can be like a supermassive black hole or like a gigantic elliptical galaxy, something very massive. And because it's there, it bends the light behind it. And then you can see images of the object that is located behind it. And those images are kind of around the lens, or depending on the configuration, you can have multiple times the image of the object. And also it has a magnifying power. So it enhances the light that you get from that object. So you see something that is hiding that you wouldn't be able to see normally. It's farther away than you would normally be able to see it because there's like more light getting to you. And also it is stretched in a way that increase your spatial resolution. So how well you see the details in the object. It is distorted. That's a little minus on that, but we have models to correct for those distortions. So it is very convenient, and Sitel can definitely be looking at those because sometimes they are extended on the sky. And so you could have the spectra over the whole lens and use it to do your model and your corrections. So definitely.
Wonderful. We have another question from the online, from Jordan Jerome. How does Einstein's theory of relativity affect our understanding of the universe through the lenses of telescopes? Does this knowledge bring us closer to grasping the meaning of our own existence? And has it expanded the comprehension of our cosmos? It's a very light question, but has it also propelled the evolution of telescope technology to new heights? And that's maybe what you're talking about with the new quantum processors that you're building in to a next generation Sibel.
Yeah. So quantum detectors, quantum computers. I mean, this is something definitely very promising. You know, those quantum detectors that I want to include in my next instrument, they are basically, they're not making images, they're counting photons. So for every photon that hit the detector, I get one line of information, you know, with timing, very precise timing, like up to like milliseconds of arrival. I know exactly when the light happened. And then I know like something about its energy, not super precise, but at least I know something about its energy. And so every photon is a bit of information coming from that detector. And you can create an image, yes, because you can like say, oh, I want all of the photons arrived in between this time and this time, stack them together, boom, you have your image. But ultimately the data is lines of every photon that touch the detector. Very powerful. And they're using those detectors also for developing quantum computers, because then you can carry information very precisely in devices. That's one thing, but that's like a very more broad and like philosophical question. So I'm going to go and touch a little bit of that. I know everybody loves astronomy, especially because of that. We all wonder, like, why are we here? Why is the universe the way it is? And and then when you start to include general relativity and all these theories that brought a much bigger understanding of what we're swimming in, and also how to process the information, and gives us an idea of how strange but beautiful our universe is. So I like to think that eventually we'll have a full understanding of the universe, but I'm very realistic. I know it won't be my generation. It might be yours. We are like in a process of improving our understanding. There's new telescopes like the WST that are pushing the limit of where we can, how far and early we can see in our universe. And those are bits of information that we didn't have before. And so I can't wait to see the publications and the informations that are going to be shared with those instruments and new telescopes. The idea, you know, of the Big Bang, you know, we evolved like in just 1 century, we evolved so much in our understanding of the universe, you know. Just a few years from now, like the theory of the Big Bang will have about 100 years. It actually, no, it just passed, like it was in 2021, right? So anyway, can you imagine that like 100 years ago, nobody knew the universe was extending? I mean, it is crazy just to think about that. So we know that the Big Bang was probably not the beginning, that there was something before, and then all theories are out, and all people that have ideas to test those theories also have to come in and help us to narrow down our understanding of the beginning of the universe. But right now we are still limited by technology. So developing new tools that have new capabilities is just a step ahead of that. And I like to think that, you know, when we're thinking of our universe and feeling so lost because we don't know what we're doing here and we don't know why the universe is the way it is, I like to think that eventually we'll get those answers. And even though it's not me, I know we're all working in the same direction, and that one day someone will, and that makes me feel good.
So we have a submitted student question asking if you're using AI in any way to sort through the images that you're getting from CITEL, or if you're planning on using it for your next project. Yeah, we did some tests. So AI, or like aspect of machine learning, not necessarily AI as people like think about when they think about AI. So it's not necessarily like a full simulation of an astronomer, but more like softwares that helps us that are built specifically for a given task using what we call machine learning. So we do use or tested those software. They're not necessarily fully implemented now, but when we have images that have like planes or satellites and other stuff in them, because it's becoming more and more common with satellites, we can identify them and reject them and take them again. So identifying defect in images. We do have also these software when we have billions of like spectra to analyze from CITEL. It's a lot of information. We need to extract the emission coming from the atoms. It takes a lot of time, hours, days of computing time. And so those those machine learning process allow us to do it more efficiently. So when we train a machine learning algorithm to do the same task again and again and again, it becomes more efficient, it learns, and it can provide us with the results quicker. So that's how we use that. Is there any avenue for this much data processing to incorporate citizen science, or is it too much that has to be done on computer hardware? That's a good question. You know, I always think there's like citizen input can be done. You always have to frame the projects to something more realistic. For instance, with signals, we have these algorithms that identify the H2 region, or the star forming region, the warm hydrogen bubbles. And so those bubbles have very weird shapes. And sometimes there's like structures that are really large that have emission, and they can be either missed in our code or included by mistake. And
at the end of the day, a code is not a human. A human eye can always identify structure a little bit better, especially if they have, if they are not regular. Well, irregular and regular at the same time, if it makes sense. Like when you see an arc that is like broken in an image, your eyes see it right away. Whereas if you want to do it by a computer, it's going to be tricky. So there are things like that that could be done with signals to improve our identification of regions and galaxies.
You ever want a guinea pig class to take part in it? I volunteer my students. Are there any other questions from David?
Yeah, just a quick question. That we know of that were formed, at what point, like hundreds of millions of years or billions of years after the Big Bang, did it settle down to where we have all the elements created by all these processes?
Oh, yeah, it will never stop. So that, like the thing is, you know, the chemical evolution of our universe kind of started almost right away, because you have at the very early universe, you had like okay, hydrogen and helium kind of formed like spontaneously after a given time when the atoms could form. And then the lithium is something that happened in the interstellar medium when they have like you have like really high energy particles that hit that gas, they can fabricate lithium. And then the other ones, and you've seen that periodic table with all the colors, are formed by astronomical like event, like massive stars, low mass star, colliding neutron star, and things like that. And there is so much space and gas in our universe that there will always be a corner where you can form new stars from out of what is available, and that star will form new material and eventually influence its environment. So we would have to go very far in the age of the universe for that process to stop. And by that, I mean extremely far, where, for instance, there's really exotic theories where if you extrapolate the age of the universe up to like billions and billions and billions of years, then eventually the expansion of the universe will be so fast that even molecule will dissolve and stars will dissolve. It will be like in a very, very far period of time, but that's possible. So ultimately, yes, this process could stop if those theories are correct. But our universe could start to contract at some point. We don't know. So that process of enrichment will always kind of happen as long as stars can form and other stars can collide and things like that.
Are you still good for a few more questions?
Yeah, of course.
Other questions from the audience here? Peter?
How did you go from like the constructive interference of the wave patterns to finding like the spectra? Like, what is that transition?
Yeah. So you have like the raw data are like interferograms, those like fringes and things that are not necessarily friendly for most people and even most astronomers. And then you process these to get those spectral cubes. So the raw cubes are images with those fringes that are taken as you move your mirror in your interferometer. So once you have those raw data cubes of images, then they are passed through what we call the data reduction pipeline, which contains a lot of different steps. So these steps, you'd have like always a block that correct for the camera itself, like the camera that used the science camera as biases, electronic biases, thermal contamination coming from different elements in the system. So light coming from stuff you're not really observing. So you correct for that. And you also take calibrations, flux calibration. So you usually have a given star that you're looking at also to make sure you know how many, like the response of your detector. So how many photons of that star equal how many light. And then you, once all of these corrections are taken, you have two cameras that have two data cubes, and then you merge the two together to have all of the light together. Since it's an interferometer, we actually subtract one camera to the other, and we divide by the sum of both. So camera A plus B minus B over camera A plus B. That's our like little equation. And then we use the mathematical tool that is called a Fourier transform. And that's that mathematical tool that passed us from from a spatial domain to the spectral domain. So instead of a movement of a mirror, it's wavelength and light colors. So if you're intrigued, you can go check out what is a Fourier transform. It actually is a very powerful mathematical tool that does a lot of other things. Temporal variation, everything that fluctuates through time. I know that they discover exoplanets using Fourier transform nowadays and things like that, just because the planet is orbiting around its stars. So you have a periodicity to the signal. So it's very powerful. And then you have a spectral cube, like the ones I showed you, that are color coded, and you can extract information from them.
Other questions from the audience here? We've got another student question message that was asking if you have your own telescope and how often do you get to just go out and enjoy the stars yourself rather than just looking at waveforms on the screen.
I used to have one. When I moved to Hawaii, I left it in Canada, but I used to have a small one. The thing is, you know, we don't necessarily spend a lot of time watching the night sky, and I kind of miss it. When I was a student and I was observing at Mauna Kea, I was doing all of the steps, so it was really nice. I was out there living the night schedule, you know, in the winter with our Canadian night that can be like 16-hour long. It was really long nights, and you could do that for 2 weeks in a row. And I was really enjoying, you know, being in the night and observing the night sky. And over here, we have a remote operated telescope, so we're not at the summit during the night. And then a remote observer is actually performing the plan that we have coded, so that we don't even have to be up at night. So it's very different. So I miss that part a lot. But we do go to the summit. Sometimes we try to stay after sunset or just after sunset, so it's still safe to drive down the mountain, because you can have icy roads after a certain time. But at least we get to see the night sky from up there for a few hours once in a while, you know. But my favorite time is just looking with the naked eye when I go to the Échappe-Moucheron Reserve, because the night sky is so dark over there. And it's often very dry, so you have perfectly, we call them photometric nights in astronomy. So photometric means there's not a lot of twinkling. So you might, you'll know next time you go outside and you're in a remote area, if the night sky is really dark, it's a photometric night. So that's we call them in astronomy.
You know, you mentioned you get 75% clear nights. We get about 7%. So we're definitely good.
Yeah.
Other questions from the audience? Yep, go ahead.
Do you get to visit the other telescopes? Do the people who work at the other telescopes collaborate? Is there a space for that?
Yeah, yeah. Yeah, thanks for your question. So it depends on the person. So when you work here, you can always trigger those collaborations. In my case, I could collaborate with some of the people working in other facilities. For example, I collaborated with people at the Subaru telescope, which is a Japanese telescope, but there's an engineer there who was from France. And he was using a spectrograph in his lab, a very powerful one on a table. And we were using it to measure very precisely our filters. We have filters that we put in the instrument. They're really beautiful, different colors. And I needed to scan it to see how well they were filtering the light. And so I could use his equipment, and he helped me operate it, and I could do this kind of things. And then we also organized a workshop not so long ago, well, a couple of years ago, on coding using Python. And so all of the telescope were involved, and we planned a 3-day workshop to exchange between different staff members what packages of coding we were using, and what tools and what tools we actually had developed, and that we were ready to share with others to facilitate everybody's life by sharing our coding. So that's some examples of collaborations here.
Wonderful. Yeah, go ahead, follow up.
A completely different question. I know at the beginning you talked about having a ceremony at the mountain. So I just wanted to know a little bit more about the relationship with the local people and maybe your personal relationship also, but the relationship in general. And also, I know like one of the headlines for today's talk was that you were the first Indigenous astronomer from Canada, but what about in Hawaii? Is there interest in higher education and in astronomy in the local population?
Yeah. Thanks for your question. So yeah, it's a very peculiar environment here. It's one of the world's best places to do astronomy. There's also a lot of cultural, social, political aspect associated with it because it's the merging of science operations with cultural practitioner and cultural sites. And also, Hawaii is very different than Canada. When I arrived here, I had so much to learn, about the community here, the local community situation, and also how the community actually access, have a word to say on what project is accepted, done, and performed on their land. And it is very different in the US than it is in Canada. So that's a learning curve for me because I really had to be familiar with that. And then I got to interact with a lot of people in the community. And some people or not necessarily they like astronomy, they like to see our science. They want to be closer to it, but at the same time, they feel like they should have more words to say for any project happening on the mountain. And there has been a lot of things said also with some protests that happened in 2019 and 2015 regarding the development of a larger telescope on the mountain called the 30-meter telescope. And I was here for some of that when that happened. And being an astronomer, being an Indigenous astronomer, I felt very sensitive about their protests. They were elevating their voice to say, hey, we are here. We don't have any people in the political component that actually listen to us and listen to our inquiries. And then they are given those permits for projects without us being involved. And it was very valuable and valid. And there's a lot of things that has changed on the island since then. And I'm so grateful for that. Because I know now that the community here have power on what's happening on the summit. And right now, just to give you an example, there's going to be the current lease for all of the facility on the summit had to be renewed in 2033. And so through these years, a lot of communication led to the building of a large committee that includes people from communities across the island that are preparing for this renewed lease to discuss the term of how science will continue on the Mauna Kea for future generations. And it's completely different than what happened in the past. And I really good hope that it will enable, the two worlds to connect. And I've spoken with a lot of people here that either are very knowledgeable about the cultural aspect of astronomy for the Hawaiian people. And when we did the equinox ceremony not so long ago, I had a lot of exchange with people here about that. And their knowledge is very well preserved here in Hawaii. I was so jealous because in my community, it's very hard to gather the astronomical knowledge. I really need to do a lot of research, whereas here, it is very alive and still taught. And so I see this kind of opportunity for them to even spread, this a large amount of information that comes from their community to the rest of the population. And I really think it's going to push some students to pursue career in astronomy once they realize how much their ancestors also contributed. And there is more astronomers in Hawaii because of so there's more Hawaiian astronomers. I know a few. They not all work on islands. Some of them are in California and others, but they are local students from here. And just like in Canada, access to school and access to opportunities is often limited for the communities. So there's a lot of work to be done. But people are more aware of it because of their voices, you know, their voices got higher with those protests and those big projects coming in. And for me personally, I always say, with the years I've spent here, I've learned the meaning of this mountain for the people here. And when you go up there, it's like a special place. You don't go there with the same state of mind as going there in a lab and a given the university. It is a sacred site. It means you have to behave in a certain way and also have your thoughts in a certain way when you go there in the right place. So yeah, I'm very grateful for that. I don't know if it answered to your kind of complex question, but.
Amazing answer, thank you.
I'm really glad I recorded this. I think that was a wonderful point to stop on. I will ask one of our students, Alakuan Miko, to give you a thank you on all of our behalf.
I feel like I don't want to be too far.
The camera's right.
Okay. Hi, I'm Alakuan Miko. I'm an Inuk student. I'm in my final semester after being here for a long time. I got accepted into Concordia University in physics. And so I'm hoping to be.
That's awesome.
To say thank you. On behalf of the students at John Abbott College at Dawson and our other local schools and the astronomy community with the RASC, I would like to thank you for sharing your experiences with us tonight. Your accomplishments and efforts in inclusivity are really important to so many of our youth, especially our Indigenous youth, and you are an example of what can be achieved. Thank you.
Hey, thank you so much. Another good news, this is great.
So thank you very much, Laurie. This was fantastic. To our online audience, thank you for joining us. To our audience here, not only thank you for joining us, but also a reminder, April 29th, International Astronomy Day. We have a talk here at 7:30 by David Schumann on space places. And if the weather is good, we will have telescopes on the field until late into the night. For tonight, help yourselves to some of our outreach material. There is food in P205 still available. And thank you. Clear skies, everyone. And I wish you all a wonderful night.
Mahalo.
Yeah, mahalo.